Okay, welcome back. This is 7-7. We're going to be doing some story problems here, so hopefully you have your book. If not, I'll try to summarize stuff anyway, so hopefully it won't matter. 7.7, applications with rational equations. And we're going to begin with the motion problems. And you probably saw these in 095. We're just going to look at them a little differently now. The formula associated with motion, d equals r times t. Okay, so d is distance, r is for rate, and t is for time. Okay, should note you could also write this equation in two other ways. So if you solved for r, you could divide on both sides by t. So if you have d equals r times t, you could divide on both sides by t. And you have an equation for rate. So rate equals distance divided by time. Another way to go about it then obviously would be to solve for t. So if you started with d equals r times t, divide both sides by r, you get t equals d over r. If you remember before we had charts in 0955, we're going to use charts again this time. It's just instead of using this equation, we'll be more concerned with this equation. Okay? But you should be able to kind of maneuver in between any equation you need and eventually work without the charts that we give you to help you in the beginning. Anyways, let's take a look at the first problem. It's checkpoint 1 in the book. And you have, let's see, you're canoeing on the Colorado River. In still water, your average canoeing rate is 3 miles per hour. It takes you the same amount of time to travel 10 miles downstream with the current as 2 miles upstream against the current. What is the rate of the water's current? Okay, so the unknown in this problem, so this is checkpoint 1. The unknown in this problem is the rate of the current, so we can give that a title, instantiate it, sometimes they call it that. We'll call it x. And there are two separate kind of scenarios. There's the rate of the boat with the current and the rate of the boat against the current. So the boat is going upstream and then downstream or vice versa. And there's two currents involved. Okay. So let's make a chart. There will be one row considering going up or I don't know which way we're going. In still water, you average canoeing rate, which is 3 miles per hour. It takes you the same amount to travel 10 miles downstream with the current. So this is downstream. So first you're going downstream. And then 2 miles upstream against the current. So upstream is against the current. Okay, so we're going to make a chart here, and across the top of the chart, we're going to put distance, rate, and time. Okay. And we set it up just kind of like the equation. Actually, we want, yeah, the distance and then rate, time. Distance, rate, and then for time, we're going to kind of fill in these blanks using this formula. Okay, so it's not a bad idea to kind of remind you what we're doing here. We'll be able to get distance and rate, and maybe in terms of x, and then we'll be able to get these using the ratio of these two. Okay, so let's go back to the story problem again and read it. In still water, your average canoeing rate is 3 miles per hour. It takes you the same amount of time to travel 10 miles downstream with the current. So downstream with the current is 10 miles. And you're going 2 miles upstream against the current. Okay. Now the rate, you kind of have to use your noggin a little bit. When you're going with the current, it's going to be the rate of the boat plus the rate of the current. Okay, so the rate of the boat is given. In still water, your average canoeing rate is 3 miles per hour. Okay, so if you're going with the current, it's going to be the rate of the water plus the rate of the canoeing, the rowing. Okay, because you have to imagine the water's pushing you, you're going to be going a little faster. So we're going to x plus 3. You may think 3 times x, but no, it's just you're going to add the speeds together. The speed of the boat plus the speed of the current will give you the overall rate. And then when you're going upstream against the current, you're going to be moving a little slower. So you can imagine it'll be the rate of the boat, and then you're subtracting away the rate of the current. We're going to suppose that it's not going to be like 100 mile per hour current or anything like that. So we'll write it that way. Okay, at the end of the day, we're going to do a division here. So we have 10 all over x plus 3. And then here we'll have 2 all over 3 minus x. Now we need to set up our equation. So in the equation, it said it took the same time to go downstream with the current as it did to go upstream against the current. In other words, we're saying that this value here and this value here are exactly the same. In other words, you can make an equation from that. You could say, okay, I know 10 all over x plus 3 is the same as 2 over 3 minus x. Let me read it again. In still water, your average canoeing rate is 3 miles per hour. It takes you the same amount of time to travel 10 miles downstream with the current as 2 miles upstream against the current. Okay, so this time and this time are the same, so they're equal. Okay. I need to solve this equation now, so I'm going to multiply both sides by the LCD. So I need to multiply by 3 minus x and 3 plus x, or x plus 3. If you do it to one side, you have to do it to the other. Okay. On the left-hand side, the x plus 3's will divide out, and you'll just be left 10 times 3 minus x. On the right-hand side, the 3 minus x cancel, and you're left with 2 times x plus 3. Distribute, so I have 10 times 3 is 30. 10 times minus x is minus 10x. 2 times x is 2x. And 2 times 3 is 6. Start collecting your variables on one side, the constants on the other. So I'll move the 2x over here. Subtract the 30 from both sides. So I'm going to have negative 12x equals negative 24. And then finally, I'll divide both sides by negative 12. And x is 2. Okay. So remember what you're trying to solve. And usually if you look at the last sentence, it'll tell you. It's find what is the rate of the water's current. So x is the rate of the water current. That's what we're looking for. And it's 2. Okay. It's we want units, so I think we're in miles per hour. Okay, so 2 mph. Okay, so you could write it up, the speed of the water, or the rate of the current, if you would rather. I don't know. Is 2 miles per hour. Okay. You know, one thing I was thinking of as I was going through here, and why is this 3 minus x and not x minus 3? If it was x minus 3, you would have 2 minus 3, which would equal -1 as your rate. And that would just mean you would be going backwards. So you really have to use common sense, and as you read the problem, kind of step back away from the math and think about it. Think about what's going on. Think about the picture in your mind. You can imagine the river and the people, maybe your friend on the boat or something like that. And usually there will be a sense of reality in that picture that you can compare to the mathematics that are sitting in front of you. And you want to reconcile the two with each other. So for instance, if you had been given the answer x equals -2 miles per hour for the speed of the current, you would probably say that's not correct, right? You wouldn't expect the water to be going in the direction opposite to where you think it's going in. You know, if it was -2, it's the current is suddenly going in the wrong direction. I would say that would imply. I'm not even sure what that would imply, but okay. So the main bullet point of that little lecture is to always try to reconcile the reality of the situation with the mathematics. Okay. Okay. Let's move on. The next kind of problem is the work problem. And the way I like to think of it is you have a fraction of work done by the first person and then if you add that to the fraction done by the second person, so you imagine there's two people working together, or they have other problems where it's like two pipes are filling a pool or something like that. So you have two things working together, and then you consider the fraction done by one thing and then the fraction done by the other thing. And together you should have one whole job completed. So if you add this fraction plus this fraction, it'll equal one whole job. Okay. In general then, we're going to let x equal the time it takes both people working together to finish the job. A will be the time it takes person one to do the job by themselves. And B will be the time it takes the second person to do the job by themselves. Okay. So in general then, I could rewrite my original equation, the fraction done by the first person. Okay. That's going to be x over a plus the fraction done by the second person, and that'll be x over b, will equal 1. Okay. Okay, so let's look at checkpoint 2 from the book. And it says, one person can paint the outside of a house in 8 hours. A second person can do it in 4 hours. How long will it take them to do the job if they work together? Okay, so let's see what information we have. One person can paint the outside of the house in 8 hours. Is that X, is that A, or is that B? Well, the time it takes the first person to do the job by himself, that's A. So A must equal 8. A second person can do the job in 4 hours. So that must be B. B is 4. How long will it take them to do the job if they work together? So that's the X, the unknown that we're looking for. So we just take these values, pop them into this equation. It's fairly simple then. You can multiply both sides by the common denominator. So I'll multiply by 8. Okay. So 8 times x over 8 is x, plus 8 times x over 4 is 2x. 4 divided by 8 is 2. 2 times x is 2x. And that equals 8. Okay, so 1x plus 2x is 3x's, and that equals 8. And then x is 8/3. Okay. So the amount of time it takes both of them working together should be 8/3 of an hour. Okay. Or if you would rather, 2 2/3 hours. Okay, so you just follow sort of the program here, and they're pretty simple. They just come down the plug and chug. Let's take a look at our next problem, our next type of problem. And we're going to start out with proportions. Okay, eventually we'll have sort of this biology problem, but okay, so let's start with proportions. And first off, we say a proportion is an equation, and on either side of the proportion is a ratio. And if you remember, that word ratio comes up in rational expressions. Ratio is basically just division. Okay, it's technically a comparison by division. So in particular, if there are 4 men and then 3 women in our class, then the ratio of men to women will be 4 to 3, or 4/3. Okay? So you're going to put the first thing in the numerator and the second thing in the denominator. Another way they can also write it is with a colon, so 4:3. Okay, so the proportion then is just an equation with ratios on either side. So you'll see something like A over B equals C over D. And finally, the cross product gives us a quick way of sort of getting rid of the fractions. You can always multiply by the LCD, but this is a quicker way. And you probably have been thinking this all along from your high school classes, that why don't we just do this? So if you have A over B equals C over D, then you can rewrite the equation as A times D equals B times C. Okay, so you just, this times this equals this times that. That's it. Okay, so let's take another look at a checkpoint. Straight from the book. The property tax on a house with an assessed value of $250,000 is $3,500. Determine the property tax on a house with an assessed value of $420,000, assuming you have the same tax rate. Okay. So you want to set up a proportion, and not only that, you want to have common units and the fractions on both sides. Okay, so what do I mean by that? It says we have $3,500 in tax on a $250,000 home. Okay, so you can write $250,000 for a house gives you $3,500 in taxes. Okay. So the ratio on the other side, when you write that, you should have the same units. You should have the house price all over the tax on that particular house. Okay, so on the other side, the house has an assessed value of $420,000. And the question is asking for the tax. So we'll just put an X in for tax. Okay. And then to solve for the tax, all you have to do is cross multiply. Right? So we'll have $250,000 times X equals 3,500 times 420,000. Then you'll divide both sides by 250,000. I don't have my calculator, so I'm just going to write it out. 3,500 times 420,000 divided by 250,000. And then if you simplify, and I do have that answer, if you simplify, you'll get X equaling 5,880. Okay. Still, we want to write up our answer. And what was that? That was the tax on this house. Okay, so the tax on a $420,000 house is $5,880. Okay. What else? Sampling in nature. So this is the biology problem I was talking about, which is kind of interesting. If you've ever seen one of those documentaries where they sort of tag animals, like they have sharks in the water and they tag them and then release the shark and they can track it or even use it to make speculations about the population of sharks. Okay, so how do they do that? They're going to catch a whole bunch of animals and tag them and then re-release them and then catch a whole nother bunch of animals and count how many tags there are. And it's from that they're able to actually solve for the total population of the animals in the wild, or the particular type of animal. So in particular then, we're going to have another proportion, and you will, capture a whole bunch of animals that are tagged and let them go. So at that point, you have a population of animals. So the total number of animals in the population. So you have maybe 1,000 sharks, and out of those 1,000, 50 are tagged. So you would put 1,000 here, total number of animals in the population. And then the numerator, you're just going to put the amount of them that had tags. So in our particular case, we've tagged 50 shark and put them back into the population where there's 1,000 of them. So we would have 50 over 1,000. So the number of sharks with tags, total number of sharks or animals with tags. Okay, so you've tagged animals, 50 of them or whatever, you release them back into the wild, and then you capture another set of sharks, for instance, and you'll have the total number of sharks you've caught, and they're going to call that a sample. So the total number of animals in a sample, maybe in your net or whatever, and then within that net, you're going to look for how many of those animals have tags. Okay, so the good thing about this is you will know how many that you originally tagged, and then when you put out your net and capture these animals, you'll know how many animals are in the net, and then you'll be able to count the number of tagged animals in the net. And the only unknown part is kind of what you want to know, the total number of animals in the population. Okay? And it's from that you can figure out how many animals are in the population. So problem 20 is about bass. And it's saying, to estimate the number of bass in a lake, wildlife biologists tagged 50 bass and released them into the lake. Okay, so the total number of bass in the lake with tags is 50. Later, they netted 108 bass and found that 27 of those were tagged. Okay, so later, they took a sample. There were 108 bass in that sample, and then 27 of them had tags. Okay, so now we're going to be able to then solve out for the total number of bass in the lake. Okay, so we just cross multiply. I have 27x equals 5,400. And then we could solve for x and get an answer to this problem. There must be about 200 bass in the lake. Okay, so it might not be exact, obviously, because of this netting problem, right? What if all the tagged fish can't make it to a certain part of the lake because of that stupid tag that's on them, you know? Actually, most of the tag fish won't ever be netted if we're fishing in a certain part of the lake, and we could be underestimating the total number of fish in the lake because of that, or something weird like that, you know? So your sample could be biased, is what I'm trying to say. It might not be representative of the true number of the true proportion, the true ratio of tagged fish to fish. Okay? And you know, you have to watch out for that thing. So my answer, anyways, long story short, and when I said my answer, I didn't say there were exactly 200 fish in the lake. You know, I cautioned the reader and I said, we think there's about 200 bass in the lake based on our estimate. Okay? Okay. The last section that I want to look at, similar triangles. So it's kind of a geometry thing. But you're going to be able to make a proportion out of it to determine some unknown information. So if you have similar triangles, okay, where the angles are all the same, so this angle and this angle are the same, and then this angle and this angle are the same, and then this angle and this angle are the same, they're called similar. And if they're similar, then you can equate ratios of the sides of the triangles. And you can pretty much do it any way you want. I'm going to say, let's say C is to B as F is to E. And you could create guides like that. You could also say something like A is to B as D is to E. So you can't, randomly pick out variables and make these proportions, but you can, so long as there's this connection. I'm not going to pick DE and then pick CA, right? I have to pick DE and then AB. Okay, so we can apply this to some problems, and even problems in your backyard you could do this with, and figure out the heights of trees. Okay, so for example, problem number 32. We'll look at this in one more example. 32 says a person who is 5 feet tall is standing 80 feet from the base of a tree. The tree casts an 86-foot shadow. The person's shadow is 6 feet in length. What is the height of the tree? So you're using shadows and similar triangles to figure out the situation. Okay, so again, I'll draw the picture here. We have a big tree, and for whatever reasons I can't get up there. Maybe there's ways you could do this with a drone now, right? So I have a big tree, and then I have a person standing 800 feet away from the tree. So I can measure that. The person is 5 feet tall. That's easy to measure. And the person is casting a 6-foot shadow. Okay, so I can set up a sort of a triangle situation. Let's make this, extend this a little bit. It's supposed to be 6 feet. And there's similar triangles here, right? So there's this big triangle. And then there's this little triangle. So it's not apparent like these problems where you have two separate triangles. The triangles are inside of each other. There's one small one here and one big one here. Okay? Okay. So we want sort of the same ratio type of sides here. So I'm going to go 5 is to 6 as this height, which is what I'm trying to figure out, the height of the tree, is to this length here, which you don't just say 800, right? It's 806. Okay, so 5 is to 6 as x is to 806. And then we can cross multiply and get our answer. So I have 6x is 430, and then x is approximately 71.7 feet. So the tree is 71 feet tall. I think we'll leave it there, and we'll just, I'll see you next time, okay?